giveaway already. So I'm looking at aging biomarkers and trying to find what does drive the aging. So some people already saw that I don't want to go old, so that's why I'm trying to really hard to work on this project to find the actual biomarkers of it. So I hope I don't look like that in 40 years, so we'll see. So I'm sponsored by Walgreens Boots Alliance, which is basically a cosmetics company trying to find novel biomarkers and novel ingredients in the in cosmetics. So I'm going to talk about skin tissue, but why do we look at the skin? We can see that there is a galaxy, there is a sun, and the skin is somewhere there. So what does it do? It acts as basically a shield for everything out there. So that's why we look at the skin. So basically it is like a roof to the house, protecting from rain to come in. But we also look at the skin because it's accessible to punch biopsies, and it's really easy to get it from different kind of sites. It's easy to get it from a forearm and from sun-protected parts such as buttock. And we really know that sun exposure has a big influence on aging. You can see this guy, I like to call him Bob, just because he usually drives to work in the morning and the sun shines from one side all the time. So you can see how drastic the influence has been on his face over 30 years. So his, I don't know which side, right or left, but this side is basically aged way more. So it has deep wrinkles and elastic material accumulation and also hyperpigmentation. But to understand what is actually happening, we need to look at the biochemical structure of the skin. So this is the roof of the house, so we can imagine this is the ceiling. And then there is the walls. So the blue lines over there is basically a walls that are surrounding, so that's basically stabilizing entire skin. So it gives the elasticity to the skin and the strength. So when you pull the skin, it doesn't break off. Yeah. So we need to look at two spaces. We need to look at extracellular space and intracellular space. So we can see that in photoprotected skin, we have a really nice walls over there. But when there is a severe sun exposure, the walls are breaking down. So the skin is getting damaged. So we know that the biomarkers up to the moment is elastic fibers are damaged, collagen fibers are damaged, proteoglycan levels are reduced. What happens to the intracellular space? So the cells become senescent. So cells are the ones that are producing these walls of the skin. So we know when it becomes senescent, it produces more enzymes that are actually breaking down the structure of the skin. So we need to know what happens with the intracellular space, what drives the senescence of the skin fibroblasts. But to get to that, we need to understand also what the skin is composed of. And everyone looks at big proteins, but look at this one. The most small protein, skin decorin, is very important to skin as well. So a healthy mice is going to have, with the decorin, is going to have a really good skin, whereas the knockout mouse is going to have really fragile skin. So we need to understand what is the composition of the skin. How do we do it? We can look at the studies out there. So there is a proteomic profiling study. There is a database such as PaxDB that collates different data from different databases. Then there is also Human Protein Atlas that does different kind of stainings of the proteins. But none of them are actually agreeing with each other. So there are still proteins lacking that we really know that are in the skin. So what do we do? Where do we go to? So most of the people out there goes first of all to PubMed or something else, maybe Web of Science. So what we did, we screened the entire Web of Science using a different set terms to actually find what the skin is composed of. And we built a database called Manchester Proteome that you can actually look at. So there's 2,950 proteins in there. So what is damaging the skin? It's UV that shines. So cysteine, disulfide bonded cysteine nucleic acid, amino acids are damaged. Tryptophans and tyrosines are damaged by UV. ROS is damaging disulfide bonded cysteines, methionines, tryptophans, tyrosines, and histidine residues. Then for glycation is also accumulating with age. It's lysine, arginine, and lysine and arginine residues that are free and are not modified. And then we can look at proteases. So extracellular space proteases are all of these, and the interstellar proteases are these ones. So I'm basically trying to rank entire skin proteome according to all of these factors. So for protease, it's going to be, for MMP2, it's going to be cleaved in this part. And for DNA, it's CT, CC, and TC nucleic acids. So what I do is I take UniProt FASTA sequences and count all of these sites that I was mentioning before for different things. Then I look at the signal peptide and propeptide, remove it because it's not in a mature protein. And I also look at glycosylation, so if it's glycosylated already, I ignore that site. And I look at the disulfide bonds and I count those ones for UV susceptibility. And come up with equations. UV ROS susceptibility is tryptophans, tyrosines, methionines, cysteines, histidines, and disulfide bonds divided by the length times 100. So it gives a percentage for each of the proteins in the skin. For glycation, it's going to be free lysines and free arginines divided by length multiplied by 100. So I can basically score each of the proteins in the skin which were susceptible to these factors. Then for Prosper, I can use Prosper, which is predicting different cleavage sites. So it uses support vector machines to predict the cleavage sites for each of the proteins where it's going to be cleaved up. So I can, again, rank which ones are going to be the most cleaved by the proteases within the skin. Then I can look, so then I can basically count all of the susceptible sites for each of the proteins together. So eventually I'll come up with top 10. Then I also look at the genome, the protein coding sites. So counting the CC, CT, and TC residues within there and dividing by the length. And yeah, this is the equation. So it needs to be multiplied by 100 to get a percentage. So then I have basically each of the proteins listed in the graph. So this is extracellular space, and we can see that the ones that I was telling you, collagen fibers, are not going to be degraded by direct UV. They're going to be degraded by proteases, whereas elastic fibers are going to be directly directed by UV. So when you go in the sunshine and you're enjoying the sunshine, if you don't put the sunscreen, this is going to be the first thing that's going to be damaged. You're going to get older because of that. But collagens are damaged with the age as well. Why does that happen? Because the DNA is going to be damaged with the time. So it's going to accumulate the silent mutations. So it's not going to be SNPs. It's not going to introduce mutation, but it's going to be silent. So it's not going to introduce misrepairs. So you can see that all the collagens are over there. Everything else is there. So it's really striking that collagens is up there. And then I found the novel biomarkers that are defensins. They might be protecting extracellular proteins from UV and ROS damage because they're very susceptible to UV and ROS. So they're like sacrificial proteins. So instead of sunscreens, this one is basically destroying itself to protect everything else. For intracellular space, metallothioneins are playing the same role. So they're protecting the intracellular space from damaging from the UV and ROS. There's everything else out there that I could explain, but that would take ages to explain. And then keratin is one of the most important parts of the epidermis. So they act as a shield, basically, to protect from UVB damage so that there is no cancer or anything, and that the UVB doesn't damage anything else deeper in the skin. And then I also found out that glycation, the accumulation of sugars, is going to accumulate on the ribosomal proteins and the histones, which is going to influence the production of the proteins with the time. So we know that it's slowing down with the time. So this is my presentation. The summary is over there. And that's me again over there. I would like to thank my group and Walgreens Boots Alliance for sponsoring this project. And I hope I'm not going to become old like that. Thank you. Any questions? Yeah?
So, if so I talk, we look at online mutagens, and I know I'm not by far the first person to do that.
Okay.
There are people who have developed these whole, like, broad spectrum ideas of what kind of damage you'd expect to see from UV light. And these are, like, done by cell lines. They're also done by looking at, like, normal tissue. They're done by skin cancer quite frequently. So I'm just wondering if you've looked at all, rather than making your own metric for UV
Yeah, so the mutagenic signatures are the ones, the CC, CT, and TC sites. So I'm basically counting those ones. So I haven't looked at the big studies or anything like that, but I know that people are reporting those sites to be mutated, so I'm looking at the sites that would be actually potentially damaged, accumulating damage with the time, and ranking the proteins to be looked at farther down the line for someone else, because I don't want to work in the lab. Does that answer your question? Okay. Anything else? Yeah. And thank you for giving me a talk as well.